Okay, hi there. I'm back from lunch, and hopefully the caffeine in the Coke, the Diet Coke, yep, I'm at that age. The Diet Coke is going to work here pretty soon because I'm kind of feeling sluggish. All right, got to get my head around some of these gas laws, right? Ideal gases and so forth, and in particular cylinders. And I want to look at an equation now that, well, two equations actually. Let me just start with showing those. Okay, so. We'll need that periodic table there right now. Okay, so first equation I want to look at is this. I'm going to burn some methane. So CH4 plus 2O2 yields CO2 plus 2H2O. Okay, balance it all out so you don't have to worry about that for right now, but let's just look at what's going on here in terms of coefficients, okay, or just total moles on each side, okay, because, well, we know that the number of moles of a gas, doesn't matter what gas it is, it'll occupy the same volume if the same temperature and pressure, okay, so I'm going to look at this and say, well, I've got 1 mole here, right? I've got 2 moles here, and so we'd say that's 3 moles of gas, right? And right here I've got 1 mole of CO2, and I've got 2 moles of H2O. I don't know why I wrote the H there, but it doesn't matter. Adding those two together, we look at that, we say, well, okay, that makes sense. I started out with, 1 plus 2 of something, and I had a reaction take place inside this chamber, and when I was done, it came out to the same number of moles, and so we wouldn't really expect that cylinder to go up or down or anything, right? So that's pretty good so far. That makes sense. So let me throw a wrench in the works. Okay. So I've got this this other reaction, and I'm going to work on the assumption that we're dealing with water vapor here. I hope that's not breaking any rules, but hey, I'm a neophyte. What do you care? All right, so let's start with this reaction this time, okay? And I'm just trying to figure this one out because I saw a side that kind of messed with my head the other day. I'm going to start with a balanced equation, 2H2O, or excuse me, 2H2 plus 2O2. Is that right? No, it's not right. I said a balanced equation. No, it's baloney. Plus 2O2 yields 2H2O. Okay? And you can check my work. It looks like, we've got 4 hydrogens here, and we've got 4 hydrogens here, and we've got 2 oxygens here, and we've got 2 oxygens here. Everything checks out so far, right? All right, so I'm going to take these 2 gases. Let's just pick a nifty color for them. I don't know if the color matters all that much, but I've got this fancy technology. I guess I could use it a little bit, right? Whoa, too big. Okay. So I've got this gas in here, okay? And we're just going to say for now that I'm dealing with a mole of each, okay? I'll put that back to normal. Okay, so knowing that that is where I started out, let's just do the same thing I did last time. I've got 2 of these plus 1 of these yields, whoa, wait a minute. Now, you would expect on this side for it to be 3, and this is what I'm trying to get my head around. So to do that, let's see what's going to happen. Okay. All right. So I've got this this other cylinder that's a lot like the one I had before it. Drew it ahead of time so you wouldn't have to suffer through it. And let's say, what does this really mean? Okay. I've got this. I've got this plunger, or I don't know what you want to call it, but there's something right here, and it's, it can slide up and down is what I want to get at. Okay, so it can go up, go down, whatever. Okay, or it could just not respond. There, that's better. Okay, so in this reaction, what's going to happen? I've got 3 moles of something, oops, and I've got 1 mole well, 3 moles of something and it becomes 2 moles of something, what's going to happen to the gas? Well, we need to understand that, I think. We're going to have to look at an equation. So let's look at the equation, and then we can predict what's going to happen inside of there. So let me put my brush back on, and I need a new layer here. Okay, so the equation that we want, or not the equation so much as the law that we want, is going to be Avogadro's law. You know, the Avogadro of the 6.022 times 10 to the 10 to the 23rd. Right? Is that right? 10? Yeah. And 6.022 times 10. Yes, that's right. For moles, I think that's right. Okay, so same guy. That's my point. Well, he also was busy doing other stuff. That's not his only contribution. And so there's a gas law that comes from his work, and we're just going to look at that now. That would be, well, in one form, it would look like this. V equals some constant, so V being the volume, some constant times A. That's the I'm just falling apart after lunch. Times number of molecules, right? So if A is constant, then I can say V over N equals A, and this could be my V1 and my N1, right? And I could say that's got to be equal to the volume 2 over N2. And I can get fancy and say that V1, that one goes up here, sorry. That's confusing, hang on a sec. So the summary, the place I just got from all that, is that V1 over N1 equals V2 over N2. And that's what Avogadro's law looks like in its more useful form, at least for me. Okay? So, what do I have so far? Well, I didn't give you the volume, so let's just say, oh geez. Well, I don't want to deal with volumes yet because I would have to calculate them. So let's just get let's say we had one. Well, no, that'll work. What am I saying? Okay. Let's say I had 1 liter of these 3 moles of gas, right? Okay. And now I have some other volume that I don't know yet, because that's what I'm trying to figure out. Okay. And I do know the number of moles, right? Because that's right here in my equation, so I can put in 2. Okay. And now that should be pretty easy to figure out. Okay. So I'm going to say that 3V2 is equal to what? 2 liters, right? And so V2, this worked out nice and easy compared to anything else I've been working on this week. That's going to be the volume, okay? Well, assuming that this was 1 liter here, okay, then this one over here, fancy graphics, is going to be, yeah, about a third lower. And I can take my fancy gas and put it in there. Maybe I can't. Oh, you know, if this were a Photoshop tutorial, I'd be really in trouble. Yeah, right. You don't need to see this part, but I'm going to do it anyway. That looks gassy, right? Now, it's actually a fortunate accident that I drew it a little bit. Well, no, actually, I don't think that has any relation. Maybe I would want to make it darker if it were the same thing, but I don't want to do that because it's not the same thing, it's a different thing, right? So in this new water vapor that's been formed out of the 2 gases, okay, what I end up with is, oh, what happened to my, this is what I meant to do. Okay, that's going to be down a little bit. Okay, oh good grief. Perfectionists just have a hard time to deal with. Okay, so now I've got the same weight of stuff, right? Because in all, whatever the molar masses come out, to, let me go back to my original equation. These 2 things still have the same amount of material in them, right? right? It's 2 moles of hydrogen and a mole of oxygen, still 2 moles of oxygen, or yeah, and 4 moles of hydrogen, right? Or did I say that right? Yeah, that's right. So it's the same weight, but the volume has changed because of the way they've combined. I had these individual hydrogens and these oxygens, and when they came together to do that, it took up less space. And so water, at the same temperature, is going to be more dense than a bunch of floating hydrogen and oxygen in the same container. Hope that helps. Bye.